Welcome to the Explainer. Today, we're going to tackle a question that's really at the absolute heart of modern AI. How do we figure out the true shape that's hiding inside our data?
So let's just jump right in. We're all swimming in data these days, right? There's more of it than ever before. But here's the thing. Raw data is, well, it's just a messy jumble of numbers. To really unlock its power, we have to see the pattern underneath it all, the structure. You could call it its shape.
And that brings us to our first big idea. What do we even mean by the shape of data? Well, it's all about getting past those individual little data points to see the big picture, the distribution they came from. It's about taking this chaotic cloud of dots and turning it into a smooth, simple story that we can actually understand.
Okay, let's make this real. What you're looking at now is a simple plot, just showing the weights of 18 different people. Each dot is one person's weight. And as you can see, it's just a bunch of numbers scattered along a line. It's kind of hard to get much from this, isn't it? Like, where do they cluster? What's a typical weight? It's not obvious.
So the real goal, the magic trick, is to transform that messy collection of points on the left into that beautiful, smooth curve you see on the right. Now that curve represents the underlying probability density. That's a bit of a mouthful, but all it really means is that it shows us where new data points are most likely to pop up. It tells us not just what we saw, but what we're probably going to see next. It's the hidden story, the true shape of the data.
And you know, this whole process, it has a name. It's called density estimation. This is the fundamental tool we use to model that shape that we can't see directly. What we're doing essentially is using the data we do have to make a really smart guess about the blueprint that created it in the first place. This is our key. This is how we unlock that story hiding in the data.
Okay, so how do we even start? Let's try the most intuitive approach, one you might even come up with yourself. You can think of it as a blurring method. Its technical name is Parzen windows or kernel density estimation, but blurring is a great way to think about it.
The idea is just brilliantly simple. Instead of thinking of each data point as an infinitely sharp little spike, what if we just blurred it out a little? We replace it with a small, smooth bump, kind of like a mini bell curve. We do that for every single data point we have, and then we just add all of those little bumps together to get our final smooth curve. Simple, right?
Ah, but here's the catch. How much do we blur? This is the critical question. And it turns out the width of our blur, the kernel width, is everything. If it's too narrow, like you see on the left, our final shape is just this noisy, spiky mess. It's overfitting because it's paying too much attention to our specific data points. But if the blur is too wide, like on the right, we just smooth everything out into one big, boring lump, and we lose all the interesting details.
Now, this blurring method feels pretty good for simple one-dimensional data, but it hits a massive, and I mean massive wall as soon as we deal with more complex data. This brings us to a super famous problem in machine learning called the curse of dimensionality. And trust me, its consequences are staggering.
To put this in perspective, let's say you wanted to use this blurring method to model something still pretty simple, like the distribution of tiny 100 by 100 pixel black and white images. To get a decent estimate, you would need roughly this many data points. That's a 1 with 3,010 zeros after it. This number, it's just so mind-bogglingly huge it's meaningless. It's way, way larger than the estimated number of particles in the entire known universe. So yeah, the blurring method, it just doesn't scale at all.
Okay, so clearly we need a much smarter approach. We can't just go blurring our way through these huge high-dimensional spaces. So, what if we changed our strategy? What if, instead of trying to build the shape from scratch, we started with a toolkit of predefined, perfect mathematical shapes?
This toolkit is a really powerful concept in statistics known as the exponential family. Think of it as a collection of greatest hits, all these well-understood distributions, each with a specific shape that's perfect for a certain kind of data. You've got the famous Gaussian bell curve, great for things like height and weight. You've got the Poisson distribution, which was famously used to model the number of Prussian soldiers killed by horse kicks each year. No, I'm not kidding. And you have many others for everything from counting words in a document to modeling probabilities.
So having this toolkit is awesome, but it's really only half the battle. We've got our data, and we've got our set of ideal shapes. The next big question is, how do we pick the right shape from the toolkit and then kind of stretch and shift it so it perfectly fits our specific data?
The core idea here is just so clever and powerful. Think of it like this. We pick our shape, maybe a bell curve, and we plop it down on top of our data. Then we start fiddling with its knobs. We wiggle its parameters, like where its center is and how wide it is, and we keep tweaking them until we find the exact configuration that makes the data we actually observed the most probable, the most likely thing we could have seen. This whole process has a name too. It's called maximum likelihood estimation, or MLE for short. And we can really just break it down into these 4 simple intuitive steps. Step 1, pick a shape from your toolkit. Step 2, place it over your data. Step 3, wiggle and stretch that shape by tuning its parameters. And Step 4, stop when you find the version of that shape that best explains the data you saw. It's an incredibly elegant and powerful way to fit a model to reality.
And this brings us to the ultimate payoff. All this hard work to find the perfect mathematical shape for our data, it's not just some abstract academic exercise, because once we have a model that perfectly describes our data's shape, we can run the whole process in reverse.
So why does this matter so much? Well, because when we have that density function, we have the data's blueprint. And what can you do with a blueprint? You can build more of it. We can generate completely new synthetic data points that are statistically identical to the real thing. And this right here is the absolute core concept behind all of modern generative AI. From the systems that create photorealistic images out of thin air to the ones that write surprisingly human-like text, it all starts with modeling the shape of data.
You know, we started with a pretty simple statistical idea, just finding the shape hidden in a bunch of numbers. But as we've seen, mastering this concept doesn't just let us analyze reality, it lets us synthesize it. As our models get better and better at capturing the true shape of the world, it leaves us with a pretty profound final thought. If we can perfectly model the shape of reality, are there any limits to what we can create?